That's the perfect transition to stage 3.
Okay.
We have now finished stage 2. We have successfully turned our food into these high-energy electron carriers, NADH and FADH2, but we still don't have ATP.
We haven't paid the bills yet.
Not yet.
We have potential energy, but not usable currency. So stage 3 is the payoff.
Oh, yeah.
And the location shifts again, just slightly. We move from the matrix to the inner mitochondrial membrane.
The barrier itself. This is where the magic, or, well, the biophysics happens. The source describes this as a coupled process.
A coupled process.
Involving electron transport and oxidative phosphorylation.
I've always found the word coupled interesting there. It implies some kind of mechanical linkage.
It is mechanical. It's one of the few places in biology where we see a literal rotary motor. But let's start with the electron transport chain.
Okay, so we have our NADH and FADH2 floating in the matrix. They approach this inner membrane.
And they hand off those high-energy electrons to a series of protein complexes embedded in the membrane. This is the chain.
Okay.
As the electrons get passed from one protein to the next, like a hot potato, they lose a little bit of energy.
And the cell doesn't waste that energy.
Not at all. The protein complexes use that energy from the electron to pump protons, hydrogen ions, out of the matrix and across the membrane.
So they are actively pushing protons against their concentration gradient, like pumping water up into a reservoir behind a dam.
That is the perfect analogy. You are building up massive electrochemical pressure behind that dam, the inner membrane.
And the electron.
The electrons eventually finish their journey by meeting up with oxygen.
Which is why we breathe. Huh?
It is literally the only reason we breathe oxygen, to act as the final trash can for those used up electrons at the very end of the chain.
So now we have this dam full of protons. We've essentially created a battery, a charge difference across the membrane. This brings us to the second half.
Oxidative phosphorylation.
Right.
This is where the turbine comes in. It's a protein channel called ATP synthase, and it lets those trapped protons flow back into the matrix.
They rush back through the gate.
And as they rush through, the physical force of their movement literally spins part of the ATP synthase molecule. And that spinning motion jams a phosphate group onto ADP to create ATP.
It effectively recharges the cell's main battery. That is the very definition of coupled.
It is.
The electron transport chain builds the dam, and oxidative phosphorylation is the turbine that generates the electricity from the water flow.
You cannot have one without the other. If you stop the electron flow, like with cyanide, the pumping stops, the dam empties, and ATP production just dies.
And if you poke a hole in the dam.
An uncoupler, yes. The electrons flow, but no pressure builds up, so no ATP is made.
Sure.
All that energy is just lost as heat.
It's a delicate, incredible system. And it brings us right back to the source's point about the high-energy molecules being readily accessible. Because stage 2 filled the matrix with NADH, the electron transport chain in the membrane has a constant fuel supply right at its fingertips.
The proximity ensures speed. When you are, say, running for a bus or even just thinking through a complex problem, your demand for ATP skyrockets. You don't want your NADH commuting from the other side of the cell.
You need it right there.
You need it right there at the membrane interface, ready to go.
So to zoom out and look at the whole picture, we start with a sandwich. Stage 1, we dismantle it in the gut. We solve that tricky hydrophobic transport problem with chylomicrons.
We get the fuel to the cell.
Stage 2, we process that fuel. Glycolysis preps the glucose, beta oxidation preps the fats, the TCA cycle strips the electrons, and we end up with a matrix full of NADH and FADH2.
The charged carriers, the full buckets.
In stage 3, we cash them in. We use those electrons to put protons, turning a microscopic turbine to mint-fresh ATP.
And that ATP is what allows your heart to beat while we're having this very conversation.
It really puts the "you are what you eat" saying into a different light. It's more like you are what you efficiently catabolize.
And you are where you catabolize. The compartmentalization is just as impressive as the chemistry.
Thanks for listening, and we'll see you on the next deep dive.